Hello everyone, welcome back to Codeverse Coders. Today we'll be starting with the lecture 2 on design and analysis of algorithms. In the first lecture, we covered divide and conquer technique, different sorting techniques. Now, in today's lecture, we'll be studying key techniques like greedy method and backtracking to build strong problem solving skills. Let's start. Today, first of all, I am assuming that you all may be familiar with the concept of greedy algorithm and backtracking. We'll be practicing numericals as well as we'll be studying some pseudocodes with respect to questions. Our first question is, in any spanning tree, if we remove an edge AB, then two resulting trees are MSTs on their respective vertex sets. And the edge A, comma B is the minimum weight edge crossing between those two sets. Based on this, the professor suggests an algorithm. Split the graph into two equal size sets, recursively find MSTs on each, and then connect them using a minimum cost edge between the two sets. Should this algorithm be used? Give a reason. First, let's visualize the question. The question says, you have basically two sets, or we can say two clusters, that are joined with the help of a bridge. When you remove this, we have two MSTs, and you recursively find the minimum spanning tree of both and then connect them. This is what the question says. But it cannot be used. Why? A very important point to note is it is a true property of MST that we should follow, which is being violated here, applied incorrectly. The property says if an existing MST and we remove an edge, two resulting components will themselves be MSTs for their respective vertices, and the removed edge will be the minimum crossing edge. However, this algorithm says the reverse. We split the graph into two equal parts without knowing whether the split corresponds to a valid cut in the actual MST. Means what we are trying to say, it is a random cut. We are seeing a random cut in between. We don't know anything about the weight, but we are saying we randomly cut it in between. Why this fails? This split may not respect the MST structure. We've discussed this. The minimum edge connecting the two subsets may not be part of the global MST. This is the global MST. That is what we are trying to say. As a result, combining two locally optimum MST does not guarantee a globally optimum MST. This algorithm is incorrect. Conclusion. Now I think you will be able to write the conclusion also. So this is what this question was all about. So let's move on to the next question. Okay, so this is the next question. So for the given graph, obtain the minimum spanning tree. So please try this question on your own. I'll first explain what is an MST. So minimum spanning tree is, like, I'll give a small example. Let's say A, B, C, D, and here we have a node. Then the weights are like this. Now when we say we connecting A to B, B to C, and C to D, are they forming a cycle? No, they are not. Have we covered all of them? Yes, we have. So this is a valid MST. Let's take another example. Let's say A to D, D to C, C to E, E to F, F to G, G to I to H, and A to B. So will this be a valid MST? Is there any cycle present? Have we covered? Is there any cycle? No, there is no cycle. Is there all are connected? Yes, they are. So this is a valid MST. But we have to show our steps when we are solving the question. So these are the steps. Please try to solve this question using these steps. First, you list all the edges in increasing order of their weight. Then add the smallest edge such that they do not form a cycle. If they are forming a cycle, you skip. And you compute the total cost of MST. So let's move on to the next question. So this one is, in the given directed weighted graph, find the shortest paths from source node 1 to all other vertices. Answer, here we'll apply the Dijkstra's algorithm. We'll compute the shortest distance step by step, starting from a source node. So basically from vertex 1, no distance, your path remains 1. You are at 1 at the moment. Then from here, you go to 6. 1 to 6. You have weight 10. Similarly, following all these steps, getting the shortest distance from 1, we'll get the required answer. Try this out. If you face any difficulty, do mention it in the comment section. Now we'll be starting with the important questions. These were all MST questions. Now we'll be starting with Huffman coding, backtracking questions. And similarly, one or two on greedy. So a file has 6 characters with frequencies given as 20, 30, 10, 20, 15, 5, a total of 100. Use Shannon-Fano coding, Huffman coding, and compare, both in terms of the total storage. So let's first talk about a Shannon-Fano coding. First, arrange the characters in descending order of their frequency. So from highest to lowest. Now try to group them. 30, 20, group them. Then you have group 2. I'll explain you by making the graph because that will be more clear. B, A, D, E, C, F. Now, when we make a graph, we split it into B, A, then we have D, E, C, F. Here we have to compute the probabilities also. So 20 by 100, 30 by 100. So this will be a 0.3, 0.2, 0.1, 0.2, then 15 by 100. Then similarly we'll compute the probabilities and then we'll continuously divide like B, then A. Now, whenever you're making this type of a graph, always remember, to your left you have 0, to your right you have 1. Similarly, to the left 0, 1. You have done this type of a problem in divide and conquer also, if you may be remembering, but here the role of probability comes into picture. So A, similarly you'll be dividing this into DE, CF, till there is individual units of each. And then suppose I have to write the code of B. What will I do is I'll use a black pen. So 0, start moving from the root, 0. Again you move 0, so your code becomes 0, 0. For A, 0, you get here. Then you move 1, 1, 0, 1. This is what is mentioned over here. Similarly, Here you move 1 for D, then 0 for this part, and then you move again D 0 1 and here E. So D becomes 1 0 0. E becomes 1 0 1. Similarly C and F. So these are your codes. Next, Huffman coding. Here we'll first combine the smallest frequencies. For your reference, I have attached the frequency count here. So smallest are F and E. No, these are not arranged in order. So C and F are the smallest. So we'll combine them making a node 1 of 15. Now node 1 of 15, node 1 of 15. Then we have E also as 15, right? So N1 of 15 and the next smallest is E of 15. We'll form N2 of 30. Always name the nodes. This will be really helpful when you are forming the tree. Then you have A of 20, A of 20, D is also 20. That is the next smallest. Now you have to see you have 30 here. Now next smallest will be 20. So you get a node 3 of 40. Node 3 is, no, this is your node 2, 30. You have B also as 30. You'll combine it to make a node 4. Then what you are left with is your node 3 and your node 4. Rest are gone into the combinations. Now you all only be left with this N3 and N4, the new nodes that you have formed. And you will get your root node. Now in this case, in Huffman coding, you draw based on sum, like 100 is your total sum. You start formation of the tree using bottom-up construction. Bottom-up construction. Like F and C are combined first. So F and C. F is 5, the smaller one to your left, bigger one to your right. Then N1 is 15 and E is also 15. N1 15, E is also 15. Similarly, you'll form the tree and you'll get the root node also. This sum criteria should be fulfilled. This is the major thing to note. Then when you have made the tree, you compare by multiplying 20 by 2. This is the frequency multiplied by the number of bits in your code. If you check, A is I think 0, 0. This is 1, 0. I think I'll have to check. So basically these are of frequency 2. So we multiply it by 2. Then 3. And we get the comparison for each of them in terms of storage for Shannon-Fano. Then for Huffman, similarly, we have the codes here. So 2, 2, 2. Here we have length of 2. Then 3 and 4. We multiply them. We get a total of 245 bits. Here 250 bits. That means Huffman coding is using fewer bits than Shannon-Fano. Thus it is more efficient in terms of compression. This line, final conclusion, very important. Next question. A group of students must distribute kids to houses connected by roads. Starting from house X, they must visit each house exactly once and return to X. If you have read this type of a problem, that is traveling salesman, it's written here, traveling salesman problem, TSP. Suggest an efficient algorithm, not brute force. Show steps and determine which if multiple teams are required. Since brute force is not allowed, we'll use the nearest neighbor greedy algorithm. First, you identify the nodes. They all are connected as we can see. Start from X. This is your X node. To signify start, I'll make this arrow. X go to A. I'll use a laser. Go to A to B, B to D, D to C, C to E, E to X. All houses are visited exactly once and we return to the starting point. Since the graph is connected and one route covers all the houses, only one team is required. Hence, using this algorithm, we get that only one team is required. Let's see this again using a laser. Please observe. 1, 2, 3, 4, 5, 6. This is also another possibility. Here X, A, B, D, C, and E, and back to X. So this was all about traveling salesman problem. It comes under your NP complete problem. So we'll discuss it in that part in further detail. Next question. Pen is not working. Propose a non-recursive backtracking algorithm. It's saying non-recursive, very important. If in the paper non-recursive is mentioned, then you don't have to use recursion like DFS and all. I'll explain what is the meaning of that recursion part in backtracking. Like this is your I comma j, you move to I plus 1 comma j and so on. So we'll discuss that. Find the maximum number of papers that can be arranged in a given sequence, unique sequence and lengths. Mention the data structures used. Also draw the state space tree. Now, if we have to use a non-recursive, so we'll use a stack instead of recursion. We try all the possible arrangements, keep only the valid ones. We also track the maximum count. We keep track of the maximum count also. Because here we have to find the maximum number of papers. We have to find max number of papers that we can arrange in a unique sequence that is given to us. So we initialize an empty stack, push an initial state, set max count is equal to 0. While your stack is empty, not empty, suppose we have Z not, we pop it. If the current arrangement is valid, then you update the max count if current size is greater. Try adding each of the remaining papers one by one. Add remaining papers. If adding a paper satisfies the condition, push new state to stack. Try understanding while the stack is not empty. First of all, you pop the top state. If this current arrangement is valid, that means if you have reached the valid state, you go on to the next part. You update the max count if your current size is greater. You try adding the papers one by one, not all together. And then if the paper that we have added corresponds to the unique sequence, you push it in as a new state into the stack Z1. Repeat until the stack is empty, till you get the sequence. Then you return your max count, the maximum number of papers that can be arranged. Let's suppose we have 1. I want the sequence 1, 2, 3. So you get 1. I am giving you a mixed sequence of numbers. So you have 1. This is following the sequence. You have 3. This is not following the sequence. Don't push it. 4. Don't. Then you have 2. Is it following the pattern? Yes, it is. 2. Is 3 following the pattern? Yes. So 3. Have you obtained the valid sequence? Yes, you have. So you return the max count 3. So this is the question. Each path start to leaf represents a possible arrangement. In actual backtracking, branches are pruned if they violate the length condition. The tree shows the general structure while valid paths depend on constraint. Now, when you'll try to draw the state space tree. Your root will be your empty solution. Levels, numbers of papers selected, and leaves will be your complete arrangement. Now, graph coloring. Graph, graph coloring says subject, you have 5 subjects, you have 5 conflicts. Conflicts means they are together, so they are in conflict of each other. We model this graph where vertices is equal to subjects and edges is equal to conflicts. Now assign color to A, that is your color 1. I think we should first draw the graph. A to B to C, B to D, C to D, and D to E. So now, as you can see this diagram, I made the diagram. So we color A first. We suppose color 1 is yellow. Now B is adjacent to A. We need a different color. So let's say blue. Now A is yellow. C can be any color. It should not be same as A or D. So let's say blue again, because that's not a problem. Then D, we can't be blue. So it can be yellow again. So we place yellow. Then E can be blue. So blue. We have to basically try minimum colors. So it is only 2 time slots are sufficient. This can come as a case study. Now, here you are given a direct question where you're given subjects A, B, C, D. There you may be given maths, physics, and all. And you may be given their connections like conflicts, who are in conflict with each other, and you have to color the graph. Similarly, Hamiltonian cycle, we'll draw the graph A, B, C, B to C, B to D, C to E, T to E, A to D, A to E. So start from A to B to D to E to C to A. This is a cycle. Here, all vertices are visited exactly once. As you had seen, just wait a second. So all vertices are visited exactly once and return to the start position. Back to your start. There may be another solution. We can try that. So A to C to B to D to E to A. This is also a valid solution. A to C to B to D to E and then back to A. There can be more than one cycle also. So this graph contains a Hamiltonian cycle. A Hamiltonian cycle is basically where you visit all the vertices. You can't visit the same vertex more than once, and you have to return back to the start position. Your n queen problem. This is part of backtracking, where you have to see valid positions for the queen. Let's draw a grid and understand. So in this PPT, I'll explain n queens properly. This slide, then queen 1, queen 2, queen 3 here, queen not q1. No queen should be in the same row, column, or diagonal. Row, column, diagonal. So let's place our first queen here. Can we place a second queen? Here? No. Here? No. Not here. But can we place a queen here? Yes, we can. Now let's see. Here? No. Here? No. No. Here? Yes, we can. Here? No. No. Here? Yes, we can. Here? No. Have we placed our 4 queens? Yes, we have. So this is a solution. 2, 4, 1, 3. Similarly, try one more solution. 3. I'll put dashes. You will have to identify. I've written the answer somewhere on this screen. So you have to fill these blanks by filling the queens on the correct places. Now knapsack problem. In knapsack problem, you'll be seeing ratios. We'll see the code later. You can refer to this numerical. This is a short numerical, but in your papers, this might come as a case study. Not such simple questions will be asked. Now, these two questions, question 1 and question 2 of graph coloring are very important. Here, let's suppose we start from A. A is your red. Now, A to B cannot be same, you choose a different color. A to C cannot be same, you choose a different color. A to E, not same, but you can repeat a color that is not same as C and A. You can choose B that you have already chosen. Now you have D. Can you choose yellow? No, because B is also yellow. You have an edge here. Can you choose red? Yes, you can. You can choose green. No. You C to D is connected. D to F is, we have yellow, we have red. What is left? Green. So we'll use a green again. And we have solved a graph coloring problem. Next question. Let's suppose we start as green. Here we can have red. No connection between B and F, so this can also be red. Now this is connected to E, so this cannot be red again. And F is also red, so let's take G again. But if A and E were connected, now it cannot be green. You have to choose a different color in that case. Then green here. Then in the second question, we have now D. This is green, but you can see here also we have green, so this can be red. Now you will get a case study. Suppose you have to start from market A, reach to market E, and correspondingly, you have to place a visited mark on each place such that the adjacent neighborhood city does not get to know that you have visited their neighbor. Something like that. You'll get a case study based on this, and you'll be given this graph, and you have to analyze and solve it. Next, this is for your reference. how a colored graph can be made with a better color also. So do check it out. This is of your Hamilton cycle that we had studied. Now, let's solve this question. Okay, first let's discuss this also. So 1 to 3, then 1 to 2 to 3 to 4, 5, 6, and 1 again. Similarly, 1 to 6, 5, 4, 3, and then 1. So these are your 2 cycles. Which of the following have an Hamilton circuit or Hamilton path, whatever you want to say? So let's say 1, 2, 3, 4, and 5. We have reached our destination. Now let's try one more path. 1, 2, I think just try. I don't think there will be another path here. Then this one we'll start by 1, 2, 1, 2, 3, 4. Now you cannot go back here. So you are stuck here. I don't think this color will be visible. I'll use red. You'll be stuck here. Similarly, this question 1, then 2, you are again stuck. Let's start from here. 1, 2, 3, you're stuck. You also try these questions. There may be a cycle present, which I'm not able to identify right now. So do try this question out. Now moving on to the pseudocodes. Very important. These will be asked. See, these type of questions have a less probability to come. But if they come, they will come as a 5 marker, 4 marker based on your application of your knowledge. Now, you have done data structures. In design and analysis of algorithms, we don't test your coding part. We test your application, how you are able to apply a concept towards a different problem. N queen problem is say function. We check the board. Use the ABS absolute function. If board of I equal to your column or subtraction of a column or I minus row, it is equal. So you return false, otherwise true. Basically, this is checking a valid move. Can any one of you guess what is it checking? Some may have guessed it, some may have not guessed it. This is checking your diagonal row concept. Column, it cannot be in the same column, row. If row equal to your n, print the board and you return. Now checking your columns, if it is a safe move, then you place the queen and move on to the next row. You are not changing the column. The column is changing with when you have placed the queen. You can't change the column before changing the placing the queen. Can't change column until queen is placed. M coloring problem. Here also essay function is needed. Now you check if your color equal to C. It returns false. You're checking your adjacent colors. If it is same as the color that is your previous color, you can't color that. So you have to return false. So node equal to 1, you have reached. You check if it's safe, then only you'll color. Otherwise, you'll move on to the next. If you have found it, otherwise you backtrack. This is backtracking. I'll write it here also, backtracking. So try to understand them rather than learning them. Like, remember there should be a isSafe function that has row check, diagonal check, column check is done here. So column check you don't need. You need to do a row check and a diagonal check. That you have done. M coloring, you have to just check your adjacent node and color based on that. Try minimum colors. That is your basic goal. Otherwise, you backtrack. Next, Hamiltonian cycle. Similarly, you just have to check visited. Either you make a visited list that you have visited this. As soon as you visit one, you put it into the visited list and ensure that it's not visited again, and you cover all the nodes. Cover all nodes and reach back. So this is basically what you all have to ensure. This code is easy, so I'll not be covering. Let's move on to the next slide. This is already covered in your data structures, if you maybe remember. If you may remember, Dijkstra's algorithm, Kruskal algorithm, and Prim's algorithm is already done. Code have a less chances, but I will not say you don't understand them. If you know how they work, writing the code will not be a difficult thing to do. In Kruskal, first you sort by weight, then you keep adding the edges, ensuring no cycle. In Prims, you try to have the minimum weight. You keep adding it and you keep adding the minimum weight, and when you reach your solution, you give the total cost. This is the basic thing that you all need to know. A visited list, like I said, very important, visited list. To keep a track if you have visited that node or not. Now, a very important code, fractional knapsack. Sort the item. Now here you all may be confused what is this ratio. So basically a custom comparator has been used here. Most of you will not be able to understand custom comparator. Now I made a video on C++STL. If you may have seen that video, I have covered this custom comparator there. But if this is not covered in your classes, do not use this custom comparator. Try to make your code yourself, because otherwise your marks will be deducted. Now these items, you can see it will be a vector. If your capacity is greater than your weight, you take the full item. Right now you have the capacity, that means, and you decrease the capacity based on the weight. I'll explain with the help of example. Let's say you have a 10 kg box. You have to, now when you put a 2 kg here, you have to now tell the code that you have 8 kg remaining. This is your 8 kg, you have taken the 2 kg. So this is what we are trying to say. Else you take the fraction and break. In Huffman coding, just remember you use a priority queue. Left is equal to pq dot top and you pop it. Top and pop. Both left and right. New node, you combine both of them and you push into the new node. Huffman coding is usually asked as a numerical question. For comparison, just know in priority queue concept. could be asked. Job scheduling. This is covered in your OSSP subject, operating system and system programming. This might not be asked in this subject, but you should have an idea of how this works. Here we assume that every task has a unit time associated. But in real life, you all also know that each task has a specific time. Let's suppose you have to go from Mumbai to Delhi. You have a specific time when you'll reach. Now, if I say from Punjab to Delhi, it will take a less time than from Mumbai to Delhi. Punjab to Delhi will take less time. So this is what I was trying to say. For jobs, you check the deadline. You have to check the deadline. Check for an empty slot. If that slot is not empty, you'll have to place it into a adjacent previous slot. Previous slot. Very important. Now this concept is what I was talking about, recursion, where it was saying a non-recursive solution. There you had to use stack, but here you can use this approach. Now, what I was saying, I comma j, now you'll understand. I minus 1 comma j, I plus 1 comma j, right I comma j plus 1, I comma j minus 1. This question or this template is applicable to number of islands, rat enemies, flat fill, and connected components. But it takes more time complexity. But we should know every solution, but we need to have the most optimal solution. So this is all what the solution was about. Don't try to apply it in every question. But this is just for some questions where time complexity is not a big issue. Because if in this subject you have this solution and you have a very high time complexity, it may lead to negative marks. So do keep this in mind. Your universal backtracking template, like I always say, I give you a template. Similarly, in AIML also, I gave you a template for BFS, DFS, and all. Similarly, for in today's lecture also, I'll give you a pseudo code. You just write it in this pattern. Backtrack. If is solution, you print the solution and return. For each choice in possible choices, if is safe, you give the state and the choice. If it is safe in this state and this choice, you make the move. And then you backtrack, and if you get a better chance, you undo the move. Simple template, nothing complex. Just know the steps. Generate all the possible solutions. Check feasibility using is safe. If valid, proceed, else prune. Undo choice. Time complexity, like I was saying, order of b to the power n. Branching factor to the power of depth, n factorial in n queen and Hamilton cycle. So branching factor to the power of depth. This is your time complexity. Similarly, universal greedy template. You sort items based on greedy criteria. Now, if you are set to write a pseudo code, don't try a custom comparator thing here. Write in this format. Solution empty at the moment for each item in items. If is feasible, then only you select and add it. You select that item and add it. You go to a grocery store. If you have to buy A, you will select A only. Now that is a separate thing. You want to buy B also, but you have to buy A. So you take A and add it to your bag. Assume this as a basket, not a bag. So you add it to your bag and you return the solution to the counter where you'll pay and take the A product. Try to visualize things. Don't try to mug up concepts. Identify the greedy choice, sort based on weight, profit, finish time, whatever, based on the criteria. It will be given in the question. Read the question 2 times and you'll find the criteria given there. Without the criteria, you cannot do the sorting. Pick the best local option, check the feasibility, and continue until complete. Order of n log n. Very good time complexity in case of greedy. Now, this is for your fractional knapsack. I told you that I'll be discussing it in the last slides, and here it is, fractional knapsack. And you have your 0, 1 knapsack. First, let's understand this concept. What is fractional knapsack? Suppose I say you have two, you go to your shop. The shopkeeper says, I will not accept any currency, but you have to get me 2 kg of grocery from your home, and I will give you whatever you want from my store. You go home, you get 1 kg rice. Now, when you go home, you have 1 kg of rice, you have half kg of wheat, and you have half kg of, let's say, maida. Or you can say corn flour. Let's say corn flour. That would be better. So now the shopkeeper says, let's talk about fractional knapsack first. The shopkeeper says, I want 2 kg. Irrespective, you give me 1.25 into 4, whatever you give me, that does not matter. I want my 2 kg. So you have 1 kg rice, half kg wheat, suppose 0.25 kg of corn flour, and then 0.75 kg of, let's say, red chili powder. So that is also fulfilling your 2 kg condition and you get what you want. Let's assume another thing. 2 kg. Now the shopkeeper says, I want something that I can sell further. I need a closed packet. Now, when you go to the market, whenever you buy a closed packet, it will be of a fixed quantity. अगर if you go to the market, आप देखते होगे एक खुली चीनी होती होगी, एक पैक्ड चीनी होती है. Okay, this is what I'm trying to say. The open sugar does not have a fixed quantity. You have to put it yourself into a packet, get it weighed by the shopkeeper, and then take it. But in case of a packed sugar packet, it will have a fixed quantity and you have to take it. You can't say, I will take only 400 grams from this 500-gram sugar packet. That's not possible. So this is what is the case of 0, 1 knapsack. Either take the full packet or you don't take the packet. He's saying I have to sell it further. Either you give me the full packet. I will take 1 kg of rice in the condition you give me the full packet. Then you say 1 kg of wheat. Okay. But you can't do something like half kg of the 1 kg packet I'll give you of wheat. Then half kg I'll give you rice. These portions he'll not accept. Now, fractional knapsack. First, you arrange in descending order of profit to weight ratio. Double is a data type. If your capacity is greater than your weight, if your capacity is still greater than your weight as of now, let's suppose you have 1 kg weight and your capacity is of 2 kg, you can take it. So you add it to your total profit and you decrease the capacity now to 1 kg is left. You have to take it. Now fractional knapsack, you can accept half kg also. I have no problem. Take fraction half kg and then you break. At last you have to give me the total profit. That is what I want. Structure of item where I have profit and weight. So this was fractional knapsack. 0-1 knapsack. Like I explained, either take full or don't take it. If they specifically ask backtracking approach, this is what you have to do. I'm not doing DP approach, dynamic programming approach. That we'll be doing later in the later classes. In lecture 3, most probably I'll be covering your dynamic programming and your string matching. So in backtracking style, knapsack, if your weight is less than equal to your capacity, you add it to your maximum profit if it is maximum. If you have fulfilled, then you return. If weight, your current weight plus the weight you are adding, suppose half, is still fulfilling, it is not still fulfilled your capacity, then you add it to your profit and weight and you increment the counter by 1. Otherwise, you simply don't change the profit and weight if you are excluding the item. Please remember this. If you are excluding the item, you do not have to change the profit and weight. Here you can see you have added value of I and weight of I. You can have a structure here also. Time complexity order of 2 raised to power n. In case of backtracking, DP case is different. Now this difference table is very important. As a 1 or 2 marker, it can be asked as A part. Differentiate between fractional knapsack and 0-1 knapsack. Now, please listen to this question carefully. This type of question will be asked in your exams. You are doing an assignment and you have to complete n questions. The question takes either T1, T2, T3, so on, time and carry M1, M2, M3 marks. So T1, T2, so on time and M1, M2 marks. You can study for a maximum of T hours. You can either, now in T hours, now you may be seeing a line above your question paper. All questions are compulsory, right? So our question says, on your paper, it's written that you either complete a question or you leave it. Choose the questions in such a way that your score is minimized. Provide a solution. So in this TRs, what you do is either you leave the solution to a question or you attempt it. Attempt plus complete it. So what do you think? You have to attempt it and you have to complete it or you leave it. Have you heard this? Either you take full 1 kg. Otherwise, I don't want your 1 kg sugar packet. This is your 0-1 knapsack. So this type of a case study will be asked. So that is all for this lecture. In this lecture, we covered backtracking, greedy technique, and we discussed different type of questions and how to understand about fractional knapsack, 0-1 knapsack, and we have seen this differentiate table also. So that is all, and do practice the questions that I've mentioned in this slide, especially the graph coloring question, Hamiltonian cycle. Those questions can be asked directly from this PPT only because these questions are important questions. If you have any doubt, you can mention them in the comments section. And if you like the video, do like, share, comment, and subscribe to my YouTube channel. So thank you all. Have a great day. Bye bye.